I am essentially having a weighted histogram. So what do I get? Let's keep it simple for the discussion. Let's say that the weights we use are unity. So I increment the bins by 1 unit for every event, particle encountered or every event encountered. And so what I'm going to get is an estimate, indeed, an estimate of P sub I. When I get capital H divided by the total number of samples, I get H sub I. H sub I is a frequency, and the limit where this the number of measurement goes to this should be infinity, I apologize. And the limit where this goes to infinity, that becomes this integral. Now, it's interesting and important to realize that the estimate H sub I is an estimate of P sub I, not of F. Simple point, but it's a very important point. And maybe for people that are really mathematically inclined, theoretical physicists, they will get this distinction very quickly. But I've dealt with young experimentalists that don't quite get the distinction. What is the distinction? Well, you can use the so-called mean value theorem from calculus. That mean value theorem tells you that when you integrate from a bound x min of the bin to the max of the bin, you get the integral of that bin, but you can write this integral in terms of the value of the function for x somewhere in the bin times the width of the bin. Right? So the value of x is within the bin, could even be on the boundary, but rarely. But it's this integral then is proportional to the function itself and the width of the bin. But the function now is evaluated somewhere in the bin, not necessarily in the middle of the bin. And if the function is linear or flat, obviously the middle of the bin is correct. If the function is nonlinear inside the bin, then you cannot approximate by taking the middle of the bin. So you have to think a little further about this. But the bigger point here is that when you do a histogram, you get H sub I. That is an estimate of P sub I, not an estimate of F. Obviously, to get an estimate of F, you only have to divide by the bin width. So we can now divide by the bin width. That will be mathematically from the PDF, that will be precise. Experimentally, that's going to be an estimator. So H sub I, lowercase h sub I divided by the bin width, is an estimator of the true value somewhere inside the bin. Okay? So the important question then is, what is the precision of this thing? So if I want to be able to do a meaningful comparison of the measurement with a theory, I have to know the precision of the measurement. So what is the precision of the measurement? And so let's do this bin by bin. Let me select a specific bin. And so the mean in a specific bin will be the total number of samples I have times the probability of that bin. The probability of that bin is this. Right? And so the mean inside a bin, in other words, the height here, the number of counts in that bin should be the relative probability of that bin times the total number of measurements. If now each of the measurements are independent of one another, one can show that what applies here is Poisson statistics. And with Poisson statistics, the variance of the number of counts in the bin will actually be equal to the mean number of counts in that bin. And so from there, now I can do error analysis. And so the standard deviation will be the square root of the total number of counts in the bin. The error on the estimator of F will be the error on the estimator of H divided by the bin width, propagate, and then you end up with a formula which tells you that the error on the estimator of F is inversely proportional to the square root of the number of counts in your experiment. You may have seen this and used this before, but this is a simple derivation of how that works. You can now think in terms of relative errors. The error on the divided by the value of the estimator itself. And so the error is what I have here. The estimator itself is this. Do simplification, you get this simple formula. So this is important because it tells you that your error is going to decrease with square root of n. Okay? So in other words, to improve your precision, if you multiply the number of events by 4, your relative precision will decrease by a factor of 2, square root of 4. If you multiply the number of events by 10, the precision will, by 100 rather, your precision will increase by a factor of 10, and only 10. So in other words, when you carry out a measurement, and if you want to have a specified or specific precision, you are able to, in principle, based on the cross-section, you are able to estimate ab initio how much data you're going to need to reach the precision that you need, that you want. You can do the same thing with two-dimensional histograms. I think I'm going to skip this. I'm going to skip this also. I could talk about curve fitting, but this is something that now people do by using packages such as Root, Mathematica, MATLAB. The only important thing that here is really the notion of errors. So given the amount of time I have, I'm going to skip to the next topic. Okay. So a moment, this morning, I showed you a formula to evaluate the error on a variable. So if I have y, a function of different values like this, what I showed you is that the variance of y is basically a sum of all these variables. And when we had dy, dxi, dy, dxj times the variance ij. Okay. So nobody argued with me that this should be telling us something about the error or the uncertainty on y. Nobody argued with me. But what is the meaning of this error? What does it mean? That's what I want to talk about now. And so I'm going to bring this up progressively from more fundamental approach. So I'm doing a measurement, okay? The variables I'm observing are stochastic by their very nature. The stochasticity may have to do with the process. So for instance, when I measure, if I put a bottle of neutrons on the table, let's assume that I can put neutrons in a bottle, and I count how many neutrons I have in the bottle, right now I would get a number, let's say 1,000,000. But in 15 minutes, which is a little more over the lifetime of the half-life of the neutron, I will have half the number. I will have 500,000. And so it means that second by second, these neutrons are going to be decaying. So that's a stochastic, the physical process itself is stochastic. But now I have to measure those neutrons. How do I measure neutrons? I need a neutron detector. So neutron has to come out of the box or decay, and then as it decays, I have to observe something that tells me that the neutron has decayed. I need a measurement. Now the measurement may have a threshold. Maybe the measurement is not able to detect all the neutrons. Or maybe it's going to double count. Sometimes it's going to measure too many. And so the measurement itself of the neutron decay is a stochastic measurement. And so in principle, every measurement has a process, what do we call process noise or measurement noise. It's a stochastic thing. And so when I study an experiment, I'm going to have to build some kind of a probability model that describes what the outcome of the measurement will be. And so there's a true value of a certain observable x. I'm going to observe some value x measured, and this value will vary stochastically. In the frequentist paradigm, the frequentist interpretation of probability, the number of counts I get in a certain interval will tell me what is the probability of finding x in that interval. If I get a distribution which is very broad, very narrow, right? I have, if this is the true value of x and I measure a PDF, I have a PDF that is like this. If it's very narrow, then my measurement is very precise. I can, for any value of x that I measure, I'm quite confident that it's very close to the actual value. But if the distribution, the PDF is like this, one measurement could yield a value here, another one here, and so on. And so in that case, one single measurement would not tell me very much about the actual value. So the actual value of x is uncertain. It has an uncertainty. But how am I going to characterize this uncertainty? There's some level of arbitrariness in doing that. And so this becomes what we call an error interval issue. Like I said, if this function is very broad, I have very poor information on the actual value of x. If it's very narrow, I have a good precision. And so the notion of precision then, or error, will really depend on the shape of this distribution. But it's still a very vague concept. Okay? What makes it even more complicated is sometimes this is not known. I don't have a formula for this. I can make a guess, and oftentimes we will guess that this is Gaussian, but we don't necessarily know that it is. So how do I go about defining an error? Well, as I just said, oftentimes, because we don't know, we will say that this function can be approximated by a Gaussian. The Gaussian will have this shape. And so 1 over square root of 2 pi times sigma, sigma being the standard deviation of the Gaussian, and the exponent e to the power minus x true to square divided by 2 times sigma square. This 2 being there, the integral of this for sigma equal 1 would give me 1 over square root of 2 pi. If sigma is not 1, then the integral from minus infinity to infinity will give me 1. And so that's how we choose this particular shape of the expression. Okay, so now I have some idea of how x might be distributed. What is it that I'm going to call the error or the uncertainty? I still have not really very well defined what that will be. Now, parenthetically, if I use a Gaussian to model errors or fluctuations, you will have to acknowledge that this has a tail that goes to plus infinity and minus infinity, and so you have to, and that's not physical. There's no measurement that can go to plus infinity or minus infinity. So this, as a model of a measurement, it has its own limitation. But we'll take it at face value for now. So now what I want is to find some specific way of deciding what I will call the error. The way we do this in practice, and the way everybody in physics does this in practice, and you may or may not be aware of what is done, but I'll tell you what is done, is that we choose an interval a to b. So x, we will say, what is the probability of x being in the interval a to b? And we will arbitrarily fix that probability to be some number, beta. That's what we do in practice. So when I carry out a measurement, x1, x2, x and so on, and now I do a statistics, I have an estimator, theta hat. I'm going to get a value for theta hat, and then I can ask myself, okay, given a true value of theta, what is the probability of getting theta hat? And what is the probability of getting theta hat in a certain interval, theta sub a, theta sub b? So the probability of finding theta hat in that interval characterizes the precision of my measurement. Okay? And so I'm going to define the error conceptually. The notion of error or uncertainty will be dependent on the interval a, b that I get given a choice of beta. To be specific, if I have a very narrow distribution, and I say, what is the probability of being in this interval? Right? And I fix the probability to be, let's say, 90%. That will give me a specific interval. And now if the PDF is instead this PDF here, and now I say, now I want 90%. Now 90% will be in this interval, qualitatively. And so by specifying 90%, I get, for a narrow PDF, I get a narrow range, and for a broad PDF, I get a very broad range. So using probability as defining the notion of error makes sense. Good. The problem now is, okay, what number should I choose? What value of beta, the integral, should I choose? So you could say, oh, I like 90%. That sounds good. Or, oh, I want to be very precise. I want to be very specific how I define the probability. I'm going to use 99%. People do that. In practice, however, we all use, without necessarily acknowledging it, we all use the central limit theorem. The central limit theorem that I is covered in the first lecture, but I didn't get to it. The central limit theorem tells me that if I have a set of measurements like this, and I sum all these variables, like this, no matter what the PDF of these x's is, the PDF of z in the large n limit will be a Gaussian. When we carry out measurements, whatever the measurement that we carry out, there's always a multitude of phenomena that are involved in the measurements. Okay? And so because there is a multitude of phenomena, each of these phenomena that is involved in the measurement contributes some value of x, some fluctuation. So at the end of the day, given all these fluctuations, we end up with something that is approximately Gaussian. So in general, the PDF of things that we measure are Gaussian, or approximately Gaussian. As I've argued a moment ago, truly Gaussian would mean that you have a finite probability of having plus infinity or minus infinity. Obviously, that doesn't happen. But the bigger point is now, in general, we can use a Gaussian, approximately. And because we can use a Gaussian, and a Gaussian is defined as x minus the mean square over 2 sigma square, using sigma as a characterization of the dispersion or the characterization of the error is very convenient. And so using 1 sigma means that if I now take the integral between minus x to x when the mean is 0, that will give me, minus sigma to plus sigma when the mean is 0, that will give me a probability content. The integral will be 68.3%. So that's what I have here. This is my Gaussian. I integrate from, and that's a normal distribution. I don't have to go in detail here. Sometimes you may want to rewrite it in terms of a precision parameter, but that's just a technical detail. Let's skip to the punchline. As I've said earlier, the expression for the Gaussian is determined in such a way that with this expression, including a 2 here, the integral will be square root of 2 pi times sigma. The expectation value of x will be the mean, mu, and the variance of x will be, by construction, sigma square. So having a 2 here and having this 1 over square root of 2 pi takes care of the normalization, and it takes care of the mean and the variance being equal to mu and sigma squared. Okay? If I set sigma square to be 1, I get the so-called standard normal distribution, which has this expression. It's pretty trivial. And I can take a cumulative integral, and here I will spend a little more time. I can take a cumulative integral from minus infinity to x. What I have here is the standard normal, where sigma is 1. And so you can verify that this integral gives you something that is related to the error function, which is defined this way. And then, of course, you can think of the complement of the error function, but that's mathematical detail. The big point here is that the cumulative distribution of the Gaussian is this function, the error function. And now that I have that, I can do a change of variable. So if I have the standard expression the standard normal, I can, for y, I can make this a Gaussian for any value or any variable x by simply doing this kind of a simple change of variable. So if y is standard normal, x will be Gaussian distributed, and it will be Gaussian distributed with a mean mu and a standard deviation sigma. And so having done that, then the cumulative integral of x or y are related to one another, and they're both related to this expression. So this expression then can be instrumental in defining the notion of error, or uncertainty, rather. This is what I have here. And so what I've done here is to take the integral of the Gaussian from minus delta to delta. I'm not specifying what delta is, it's a number, but you can now show very simply that this integral of the Gaussian PDF, I labeled it ds for double-sided, so I integrate from minus delta to delta, and so it's related to the error function delta over square root of 2. So this function is plotted here as a function of delta. So when delta equal 1, that's one sigma. I have a probability content of 68.27%. So 68.27%. When I get to delta equal 2, I have 95. Delta equal 3, I have 99.7, and so on. So because of the CLT theorem, it's useful and convenient to use Gaussian. Because it's convenient to use Gaussian, and given the expression of Gaussian, we usually think in terms of 1 sigma errors. And so 1 sigma errors is such that the probability to measure x as a probability of 68% of falling between minus delta and delta. That is minus 1 sigma to plus 1 sigma. And that's the true meaning of the errors we use in physics. Typically, all the publication we have in particle physics, nuclear physics, they all use 1 sigma. There are some fields where they like to use 2 or even 3 sigma. But in general, in particle physics, we use 1 sigma. And so that is our standard. Okay, so maybe I convinced you of something, but now I'm going to question what I just convinced you of. Okay, so I define what's known as a confidence interval. I said I'm going to take the integral of my PDF from some minimum value to some maximum value. This has a content beta, and I arbitrarily said I'm going to do it from minus delta to plus delta because it's a Gaussian. But in general, it's not necessarily a Gaussian. It's not always the case that the central limit theorem applies. It's not always the case that you have a Gaussian. Sometimes the PDF that describes a measurement is far more complicated than the Gaussian. So what do you do in that case? Well, you can still use the notion of probability content, okay? You can still say, I'm going to fix beta, and now I have to choose an interval. I have to relate beta to some interval. But if I am taking an integral, let's say I have this. I want to choose a range such that the integral of this PDF within the range will be beta. There's an infinite number of ways to do this. It's possible that I could take this range instead and still get beta. Or I could take yet another range and still get beta. So unfortunately, defining the value of beta is not enough to tell us what the range is. It's both good and bad. In general, we don't worry too much about this because, and if you're a theoretician, most likely you don't care, and good for you. But if you're doing an experiment, you may have to care about this. In what context would you care about this? Let's say that you're measuring the mass of the neutrino. Okay? I apologize. This is from Leesburg, Virginia. No, nobody in Leesburg, Virginia. Where was I? Right. And so in general...
You were saying that you know how to measure the mass of the neutrino.
Ah, yes. So it's easy peasy. So, while there are experiments out there trying to measure the mass of the neutrino, we know that the mass of the neutrino is very small. We know that from oscillations in particular, right? So, when I measure the mass of the neutrino, if my experiment is very precise, I might be so lucky as to say the mass of the neutrino is 1 eV plus minus 0.01 eV. That would be if I'm very lucky. We haven't reached that kind of precision yet. The kind of precision that we're measuring now is that we can say it's close to 0, but not 0. And there's an important distinction or an important subtlety here. I know that the mass of the neutrino cannot be negative, right? I'm not aware of particles that have negative mass. You know, you put it on the table and it reaches the ceiling. So the fact that the mass cannot be 0 affects how you can quote your error. If you measure 1 eV for the mass, let's say your experiment reveals you go through all the motion, you get 1 eV, and your precision is 1 eV plus minus 5 eV. Well, it works on the positive side. You could say it's okay to have a mass of 6 eV, perhaps more, but it's not okay to say that the mass would be minus 4, minus 5 eV. So how do you get around that? Well, you get around that by choosing an interval, a confidence interval that is not symmetric. And you say my interval of confidence will start at 0 because I know the mass cannot be lower than 0. And then I will choose the probability content to go as high as I need to go to achieve, let's say, 68% or 90%. So that's how it's done. So it's a single-sided confidence interval. So there are many ways to do this. But in general, in the greatest generality, we're going to say the confidence interval will be defined by probability of content beta, and I'm going to integrate from A to B. And obviously, as I just told you, there's an infinite number of ways I can do this. And so that's a problem of interval estimation. I'm going to skip some details. If the PDF of the measurement of x is a Gaussian, then I would be so inclined as to choose an interval A to B that I would express in terms of sigma, but I don't have to do this. In general, I can let A and B be completely arbitrary, and there's an infinite number of ways I can get beta. How so? Well, this integral here is the difference of cumulative integrals, and I showed you that the cumulative integrals are related to so this is really I have it here. So I can take a cumulative integral from minus infinity to b, and if I subtract a cumulative integral from minus infinity to a, is what I have here. And so that's the cumulative integral to b to a, and so the probability content is this much. So if I fix a and I choose beta, I have fixed b. If I choose B and A, I have fixed beta. So there's an infinite number of ways of doing this. Okay. So for this to be useful, then I'm going to choose beta. Let's say 68%. And now I could envision an interval that would go from the mean plus delta 1 and the mean plus delta 2. Okay? And so that's an integral. The probability of finding x in the interval mu plus delta 1 to mu plus delta 2, given that I have some idea of what sigma could be. Okay? And so that's just this integral here. Now I can do a change of variable, shown here, x minus mu over sigma. If I plug that in, then my integral becomes just this. And so no matter what the actual PDF is, no matter what the value of sigma is, I can always come back to this difference, provided I have some idea of what sigma is. And so in general, if I know it's Gaussian, and I know sigma, or approximately know, I have some approximate knowledge of sigma, I can always come back to this expression, and consequently, I can always relate the probability content delta 2 and delta 1 being defining the interval. So that's if I know the mean. Let's say I don't even know the mean. Oh no, sorry. Confusing myself sometimes. Okay. What's the big deal here? Okay. Why am I doing this? You're measuring an suppose you're interested in the mean. Okay, you want the mean. And so you're going to repeat your measurement, and you're going to see some distribution, or maybe you're not going to repeat your measurement, but you know the precision of your measurement. Hello. It's okay? So suppose that you know the value of your measurement. What can I do with this? So here I have taken an integral from delta 1 to delta 2, and then here I did a change of variable, so it changed it from delta 1 over sigma to delta 2 over sigma. And that gives me this difference of cumulative integrals. So what I have here is the probability of x being larger or equal to this, and the probability and as well as smaller than mu plus delta 2. Now I have two inequalities. I can invert both of them, and so I can rewrite this inequality as mu being less than x minus delta 1. And this one I can rewrite as x minus delta 2 being less than mu. What have I done? I have changed the probability content of measuring x into a probability content of measuring mu. So what I have here is an interval for mu. Right? If I know sigma, then I know beta for that given interval. Okay? And so that specification gives me an interval now for mu. And so beta now gives me the probability of finding mu in this interval. What have I achieved here? I have transformed the width of the PDF of x into a width or an error for mu. And so experimentally, we do this all the time. We don't even think about it. You say, I have so many counts. Let's say I measure 100 counts. And I say the error is square root of 100. And so the implication is that the cross-section that is related to this will be 100 plus minus square root of 10. Right? That's what we do intuitively. Why can't we do this? We can do this because this inverts. I started with a model of my measurement. I said I have, this is a subtle point, but it's a very important point. I have a model of my measurement. The model here is assumed Gaussian with a sigma of with a width of sigma. When I say probability of beta, it means that if I knew mu, I could tell you that x. Whoa! I'm losing the capacity to use this old technology. So this width, if I choose beta, let's say to be 68%, that determines this width for a symmetric interval. What I'm telling you now is that I'm carrying this experiment once, and I get a value of x. And I'm now telling you that this value of x can be used as an estimator of mu. I'm going to write that my estimator is actually the value of x that I just obtained. And we do that all the time. And what is the error? This error is determined by the probability content beta. And so if I start with a Gaussian and I know the performance of my experiment gives me a certain sigma, I can calculate for a given beta, I can calculate delta 1 and delta 2. I can make that a symmetric interval. And having made this interval symmetric, now I can invert. I have this interval here. Let x greater than this, x less than this. I now invert this. And so I have x minus delta will be less than mu. X minus delta 1 will be greater than mu. So the value of x that I've measured gives me an estimator of mu, and that estimator is guaranteed to be in this interval with a probability of 60%. And so if I now measure x, I can use that as an estimator of the mean, and this estimator will have an error that I can determine from this formula with a specific probability content. And if I choose this probability content to be 68%, then this is plus minus 1 sigma. We do this every day, but not everybody realizes what they're doing. And most of the time it's okay. So just to articulate this a little more, what I've just said is that in general we're going to take an interval with a probability content of 68% that will correspond to an interval of plus minus 1 sigma. And so obviously even with that definition I still have some arbitrariness. I can choose the alpha point or the alpha point plus beta, and that's going to be a probability content of beta. And so there's a large way of number of ways of doing this. If I don't know the mean, which is what I can assume, then I can do, let me skip this. It's too detailed. So what I've articulated here is that I have an infinite number of ways of choosing my confidence interval. So if these are my boundaries, I choose the probability content to be beta. I would have alpha here, and here it will be 1 minus beta minus alpha, which is not necessarily equal to alpha. I could choose the interval to be symmetric, So that will lead to what's known as a central interval. And again, this is something that we always do, or most of the time do, in our measurements. We assume that we are taking an interval that is central and symmetric. As I've argued a moment ago, if you're trying to measure the mass of a neutrino, it's conceivable that this will make no sense because you cannot have an uncertainty that would go negative. When the distribution is not Gaussian, and this is again a very subtle and not so important point, but the central interval is possibly not the best interval you could quote. And so let's imagine that the PDF of your measurement, characterizing your measurement, would be like this. If you use a central interval, you would be inclined to choose something that is symmetric. It will have some probability content, but that may not be the best interval to quote. You might be doing better if you choose the shortest interval. And so for a given function like this, you can reason that there will be an interval such that it's shorter than possibly a central interval, but that's again a detail. The same type of reasoning we've done now with a measurement of one parameter, I can now repeat with a measurement of several parameters jointly or at once. And so let's say that I'm fitting a straight line. A straight line will be defined by two parameters, A0, A1. Right? I now have two parameters to my measurement. Both will have their error. And so the concept of confidence interval exists here again, but instead of having an interval, now I have a confidence region. And so it's illustrated schematically here. I have theta 1 hat minus theta 1, theta 2 hat minus theta 2. So these theta 2 and 1 are the parameters of interest. And now I have a confidence region. Sometimes the confidence region is going to be a circle. Sometimes the confidence region will be shaped like this. Why would it be shaped? Or if you choose the confidence region to correspond to a certain probability content, again, in principle, there's an infinite number of ways to do this, but there is a particular shape that will give you the minimal surface, and that will correspond to the minimal confidence region. If all these parameters are behaving according to some Gaussian or approximate Gaussian, in general you could define confidence regions that would also be accordingly Gaussian. There is a subtlety that will take place here. Oftentimes when you have two parameters like this, when you, let's say if you were fitting a straight line, you might encounter cases where the value of A0 is not independent of the value of A1. So there will be some correlation between the two. In other words, there would be a finite covariance between A0 and A1. If that's the case, then this probability region now can be written in this fashion. So if everything is Gaussian, you can have a quadratic form like this, where this object here is the inverse of the covariance matrix between the parameters. How much time?
Now 15 minutes.
15? Okay. I will cover one more topic. Let me finish this topic. And so if I can do this, this representation like this in terms of the inverse of the covariance matrix, And if this is Gaussian, and I think I have my Gaussian here, right? When I take a certain contour, I can find a contour such that this will have a certain probability content. And so because I have a simple expression, then it all boils down to, I have a function q of theta hat given the true value, which is this quadratic form. And so it turns out that this Gaussian form is equivalent to a chi-square distribution. And then you can calculate the integral of the chi-square distribution given some bound k beta, and it will have a probability content beta. And so that's one way of arriving at multidimensional confidence regions and defining them in a very precise mathematical way according to some probability content. What that means in practice is that you're measuring a certain phenomenon. Maybe you're measuring the slope of a relationship between x and y. So you're getting values for a0 and eta1. Here they're listed at theta1, theta2. So it may well be that theta1 and theta2 are the true values. And when you do the experiment, because you have fluctuations in the measurement, you will get a contour like this for the values of theta1 and theta2. This contour will have some probability content beta, which will be determined by, as I said, technically by a chi-square distribution. So you can calculate the size of this contour based on a choice of probability content. What you have to be aware of is sometimes this is a circle, but not always. And so if it's not a circle, it means that if theta1 is large, theta2 would also be large. And so your error then cannot be stated, you cannot state the error independently for theta1 and theta2 separately. You have to do this ellipse. You have to draw this ellipse. I mean, this seems trivial, but imagine that the ellipse would be with another orientation. It would mean that if theta is, when you say theta1 is large, it would mean that theta2 is small, and so on. Okay, so but anyway, the bigger point that I was trying to get to here is that if this is the true value, performing the experiment repeatedly would mean that, let's say 68% of the time, theta1 and theta2 would be within this circle. And because of that, and because essentially what we've done for one variable, I can invert the relationship between the measured values and the true values. And so now I can say, if I go back here to this expression, because this is completely symmetric, you know, whether I choose theta hat or theta, this is perfectly symmetric, right? And so I can swap the two, and because I can swap the two as I've done before with a single variable, I can say, okay, this is my measurement. I get an estimator theta1 hat, theta2 hat, and the contour that I can calculate based on a probability content, which was this one, now will be the contour for theta1 and theta2. So given a measured theta1 hat, theta2 hat, the contour for theta1, theta2, the true value, will be the same contour. Okay? Again, we do this routinely in our work, but we don't always acknowledge where this comes from. And this, I thought this would be interesting to tell you where this comes from. And this is the point of this slide here is to tell you that depending on how you want to quote the error, you have to be a little careful. If you have the error contour, the confidence region, and you have established that the confidence region has a certain probability content. Now, if now you wanted to say this, the error on theta 2 would be from here to there, you have to realize that this interval now does not have the same probability content. And this interval here to here does not have the same probability content. So if you want to be picky and formal about defining errors, you have to take into account these things. We rarely do, but if you wanted to be, that's what you would do. I want to cover one more topic connected to this, and coming back to measurements where you have a boundary. Say the mass can only be positive, or you're looking for a predicted particle that has never been observed before. I spent 5 years of my life looking for strangelets. We didn't find them. So we can say that the cross-section for producing strangelets is 0. But it really isn't 0 because my measurement had a finite precision. It can be negative, but it could be a little larger than 0. I measured 0, but it could be a little larger than 0. So I have some uncertainty. And so whether you measure the mass, a cross-section, or phenomena that have a boundary, whatever they are, the boundary might be, you cannot use a two-sided interval. You cannot use a symmetric interval. You have to use some other kind of interval. And again, just to be picky and to be formal about this, you can end up in circumstances that are a little tricky. And I will begin the discussion with what the problem is, and then I'll show you mathematically what this means. And so let's assume that I'm measuring the mass of the neutrino, or trying to, and the mass, let's say that the mass that I get, technically speaking, is 1 eV, but my precision is 3 eV. So I get something that would look like this. Obviously, this is not non-physical region, right? I know it's non-physical. And so because it's non-physical, it doesn't make sense to say I have measured 1 plus 3, plus minus 3. And so in practice then, I could say the confidence interval is 0 up to some value. And I could say this, I'm going to, given the PDF that I have, I'm going to say, I'm going to choose this interval, the maximum value of this interval, such that the interval has a probability content of 68%. So instead of using plus minus 1 sigma, which has a probability content of 68, I'm going to choose an asymmetric interval which has the same probability content, but is remaining physical. So it will start from 0, and so instead of going from here to here, which would make no physical sense, it will go from 0 to some upper value. And that's what people do. When you try to measure the mass of something that has possibly 0 mass, you use a one-sided interval. If you're trying to measure the cross-section of something that has never been observed before and you don't find it, you will say the cross-section could be as low as 0 and as large as some value. Now, sometimes you actually find a cross-section which is distinct from 0. And so that leads to what's known as flip-flopping. If I measure 1 eV and I say my error is 3 EV, if I assume Gaussian, then I realize, okay, this makes no sense. I can't use a two-sided interval. I'm going to use a one-sided interval. And now if I measure, let's say I measure 5 EV plus minus 3. Now I can use a double-sided interval. So there's common practice in a lot of experiments to say, okay, I look at the value that I have, I look at the error that I have, and now I decide whether I have a one-sided interval or a two-sided interval. And this is bad science. Because why should you decide after you've looked at the measurement what the interval should be? You're doing some bias in your reporting of the interval. And so some people gave this a lot of thought, and this kind of discussion is kind of a subtle point, but it becomes relevant when you're trying to extract and squeeze out the best precision that you can out of an experiment. And so this solving this problem, this so-called flip-flop problem, is achieved with the so-called Nyman construction. And we don't use that in Alice, I don't think, but it would be nice if we did.
I think we did already.
We did? Okay, good. Okay, very good.
I have to check because it was very tricky.
Yeah, it is tricky. So when I choose an interval, I could choose a central interval that would have would be two-sided, or I could choose a one-sided interval that would stay from, let's say, from 0 to some upper value. And what am I talking about? What I'm talking about is defining a probability content beta, knowing that the true value is theta, and that when I have a true value of theta, then the value that I measure can fluctuate down to some lesser value or fluctuate up to some upper value. Okay, what do I mean by this? Let's suppose that the true value is theta 0. So this axis here is the true value of the parameter. This axis here, horizontal axis, is the parameter that I measure, the estimate. And so given a understanding of the experiment, I can, if I know the PDF of my measurement, I say, okay, I have theta 0, it being the true value, with a certain probability content beta, then theta hat will be in this interval with a probability content of beta. What I'm going to show is that now I want to flip this interval in theta hat to become an interval in theta. I've already done this for a Gaussian, and nobody screamed. What I'm going to show you now is that I can do this for any type of distribution, not just Gaussian. And given a measurement, I can take my interval in theta hat and convert it into an interval in theta. But you already see from this graph that there is a potential for trouble. If the true value is unknown, as usually it is, depending on the true value, this interval, for a given probability content, this interval may be changing. All right. So your precision may depend on the actual value of theta. So what we have is not just a confidence interval, but it's a confidence belt. What was that? 0 time. Okay. All right. So the name and I'll try to go quickly through this. So the name and construction is to say that we can invert the relationship between theta and theta hat, and by defining a belt or a region like this. And because we can do this construction, the interval in theta hat can be transformed into an interval in theta. And that's illustrated here, as I've already said. Now, I'll just define the problem, and then if you're really interested, we can discuss it afterward. If I have a central interval, let's say I have a process that I have a measurement that is Gaussian, I could define this belt here. Okay, so that would be a central interval plus minus, let's say, 1 sigma. Well, it's not quite 1 sigma on this plot, but it's okay. If instead I decided to be a one-sided interval, the minimum would be this dashed line, and the maximum would be infinity. And these would have the same probability content. The point of this plot here is that I have 0. So if theta hat was a mass, I would have to flip-flop between a central interval to a one-sided interval, depending on the value of theta that I get. And that's just not right. You can, based on this construction here, you can show that, just to give you an example of how absurd this becomes, if I measured somehow -2, my interval here would have 0 probability content. It's not impossible that I measure -2, but according to this construction, I would have 0 probability content. So this is known as a problem of non-coverage. And so there is a technique to go around this, which is known as the Nyman construction and the Feldman and Cousin method, which I'm not going to have time, but if you're interested, we can talk about it afterward, where you, instead of using a central interval or a one-sided interval, based on the result that you get, you can ab initio define an interval which is going to be a slanted interval like this. This looks arbitrary, but it's not. There's a procedure to achieve this particular very specific interval, knowing the performance of your experiment. And that's known as the Feldman and Cousin method. So let me stop here. I wanted to give you an impression of what errors are, because we manipulate, we estimate errors all the time, but oftentimes, particularly with students, they don't really know what the meaning of an error is. So it's important to have a grasp of what an error means. It's usually defined by the probability content, even though we don't express it in practice. Okay, that's it. Thank you.